Up until this point, we've used Boolean algebra to minimize equations. In these next 4 modules, I'm going to talk about how to use 2 other methods to minimize equations. These 2 methods, Carnot maps, or K-maps for short, and the Quine-McCluskey method, are based on the Boolean theorems that we've been using to minimize equations by hand. So in order to use these other methods, Carnot maps and Quine-McCluskey method, we need to understand the Boolean theorems that they're based on. And we've done that in the past few modules and past few homeworks by working through those Boolean theorems by hand. So today we're going to talk about, I'll introduce K-maps, and we'll talk about K-map rules, as well as K-maps with not just ones and zeros, but also don't cares. And then I'll briefly discuss multiple output circuits, as well as other signal values, X contention and Z floating. So we've used X for don't care. We're overloading that symbol to have it mean also contention. So we'll talk about that at the end of this module. So Carnot maps, K-maps for short, are used to minimize our equation graphically. K-maps use graphical versions of combining to combine terms. So here's a truth table with 3 inputs, A, B, and C, and an output Y. And Y has some function here. So we can essentially draw our truth table graphically, where we have each box corresponding to a row in the truth table. So this is the 0, 0, 0 box. So we have A and B on this top axis and C on the vertical axis. And so the 0, 0, 0 row corresponds to this box here. 0, 0, 1 corresponds to the box just below it. We have 0, 0 for A and B, and 1 for C. 0, 1, 0 is here. 0, 1, 1 is here. 0, 1, 1. And then something strange happens. We have the 1, 0, 0 box, but it's not here. 1, 0, 0, we jump over a column and put the 1, 0, 0 row on the top right. So the 1, 0, 0 row corresponds to that box. 1, 0, 1 corresponds to the box just below it. And then we come back to the 1, 1, 0 box, 1, 1, 0. And finally, the 1, 1, 1 box. So let's take a look at the minterms associated with these rows. So 0, 0, 0, that minterm is A bar, B bar, C bar. 0, 0, 1, A bar, B bar, C. 0, 1, 0, A bar, B, C bar, and so forth. And so you can notice that these minterms in neighboring boxes differ by a single literal. So going from this box on the left, for example, the 0, 0, 1 box to the 0, 1, 1 box, these differ only in the B term. Likewise, if I go from this box to the next box, those differ only in the A term. And it also works going vertically. So this box at the top, the 1, 0, 0 box, A, B bar, C bar, and this box just below it, A, B bar, C, these differ only in the C term. Well, and that's a useful property for us. So if we have some term, A, B, or A, B bar, that differs only in a single literal, in this case the B literal, and B bar literal is what differs, we can combine those terms and just get A. And so we're going to do that. First of all, we enter the value of y, of the function, into our k-map here. This is our k-map. So this one goes into the 0, 0, 0 box. The next one goes into the 0, 0, 1 box, 0, 0, 1 box. And the rest of the boxes contain zeros. And now we can circle ones in adjacent boxes. So we circle those two ones, and that's basically effectively saying, well, y equals a bar, b bar, c bar, or a bar, b bar, c, those two min terms. Well, those two terms are the same except for in the c position. And so that just is equal to a bar, b bar. And so we can see graphically that this circle only covers the a low and b low, a0 and b0 case, so a bar, b bar, but it covers both forms of c. So c is not in the equation because it covers both forms, that circle covers both forms of c. But the circle only covers the zero forms of a and b, so a bar is in the equation ANDed with b bar. And again, this is the longhand way. We're now no longer doing it that way. We're doing our minimization graphically. So we circle adjacent ones. Again, using combining, we can see, hey, that top min term included the c bar form of c, and that bottom term included the c form of c. The common term was a bar and b bar. That's the only form of a and b included in that circle. But c has both forms covered by the circle, so c is not included in our term. And we can graphically reduce it to y equals a bar and b bar. Let's do another example. Again, you don't need to write this out in general. This is shown just for your convenience to remember, oh yeah, each of those boxes corresponds to a min term, and if I circle adjacent boxes, I can get rid of literals in my product term. So let's go ahead and enter this truth table into our k-map. Again, we'll draw that line to help keep us aligned. This 0 goes here in the 0, 0, 0 box. This 1, or this 0 goes here in the 0, 0, 1 box. This 1 goes here in the 0, 1, 0 box. This 1 goes here in the 0, 1, 1 box. And now we have to do something kind of strange. This 1, 0, 0 box, well, if we look at our k-map, almost goes in counting order, 0, 0, 0, 1, but the next column is not 1, 0. Well, why is that? If this next column had been 1, 0, these adjacent rows would have differed in the a term. A changes from 0 to 1, and the b term. B changes from 1 to 0. But we can't have that because adjacent columns have to be differing by a single term. In this case, when we reorder it, they differ only in a. B stays the same from one column to the next. So we number the top row of our k-map in this order. This is also called a gray code because adjacent values differ only in a single bit position. So when we're entering our k-map still goes in counting order. So 1, 0, 0 is not here. We have to jump over a column and enter it here. So this 0 is in the 1, 0, 0. box. This 0 is in the 1, 0, 1 box. And now we go back over to the 1, 1, 0 box, which is here. And 1, 1, 1 has a 1 in it. So now we've entered our function into our K-map, and now we can circle adjacent ones. So these two ones are adjacent. Well, those correspond to these minterms, and we can see that this really corresponds to B and C. If I ORed these two minterms together, A bar and B and C, or A and B and C, I just get B and C using combining. And now I can also circle these two ones. It's okay to reuse a minterm if it helps me reduce the product term. So here I circle these two. Again, idempotency, I can reuse that minterm as many times as I want. So these two reduce to, well, A bar B C bar, or A bar B C just reduces to A bar B. Now going directly from my K-map, I can see that this circle, this vertical circle, covers just the 0 form of A, so A bar, and the true form of B, 1, so A bar B. But it covers both forms of C, so C is not in the equation, in that implicant, in that product term. In this circle, this horizontal circle across these two ones, well, that one has just the true form of C, so this is going to have a C in it. And let's see, has only the true form of B in it, but it has both forms of A in it, A bar and A, so it's just going to include B and C. Then we're going to OR those terms together. Y equals A bar B, that implicant, or B and C, this implicant. Could we have done this longhand using Boolean theorems and axioms, particularly combining? Sure, would have worked out the same. But graphically, tends to be a little bit faster. So here it is written out nicely for you. So let me show a common error at this point. So common error is to go and maybe circle these two and say, okay, great. Now I get my B and C term. And then here's the error. The error is to say, okay, now I'm going to circle that one. That's not logically incorrect. I'm going to get, for that single one, I'm going to get A bar and B. So 0, A bar, and 1, B, and C bar. But it's not minimal, because I could have made that circle bigger, like we showed in the correct version of this. This is the correct version. This is incorrect. The correct way to do this is to make the circle as big as possible to reduce the number of terms, to use combining. And now I can get rid of that C term and just make it A bar and B. So because both complement and true forms of C are in that blue circle, C does not need to be in my implicant, in my product term. Again, so this is a common error. This is incorrect. Remember to make your circles as big as possible. So the correct version is, in fact, our big circle that corresponds to this implicant, this product term. So let's come back to some K-map definitions. We've talked about these before. Let's review them briefly. A complement is a variable with a bar over it. A literal is a variable or its complement. An implicant is a product of literals. And now we're going to define this new term. Prime implicant is an implicant corresponding to the largest circle in a K-map. So a prime implicant has the fewest number of literals in that product term because the circle is as large as possible. So let's talk about K-map rules in general. Every one must be circled. It could be circled multiple times, but it must be circled at least once. So every one must be circled, and it could be circled multiple times, but it has to be at least once. Each circle must span a power of 2 boxes. So 1, 2, 4, 8, etc. And each circle must be as large as possible, so we can have a minimal form of our equation. Now, a circle may wrap around the edges. Let's take a look at a K-map. Here's an example K-map here. It has 3 inputs, A, B, and C. A and B across the top, C along the side. So 0, 0, 0, 1. Remember, gray code order, so they differ, and neighboring squares differ only in a single variable. So 0, 0, 0, 1, 1, 1, 1, 0 across the top, and 0, 1 along the side for C. And let's put in some function. Here's a function like this. And we may immediately, this isn't correct yet, but we may go like this and say, okay, I'm going to circle my ones, my power of 2 groups of ones. So in this case, I have groups of 2 ones. And then I'd write my implicant for that. This is A and B bar. So A and B bar. C has both the true and complement form covered in that circle, so it's not part of the implicant. And for this circle on the left, we get A bar and B bar. A bar and B bar. Again, C has the true and complement forms covered, and so C is not part of that prime implicant. So we may do this and then write our equation. Y equals A bar, B bar, that term, or A and B bar. And at this point, hopefully you realize, wait a minute, I could use combining again. That's some term, B bar and A bar, or that same term, B bar, and the true form of A. Well, I can use combining there and say, well, that's just equal to B bar. Why didn't I get that graphically? Well, the problem is that we didn't wrap around the edges. So if we notice, if I go from this edge over to wrap it around over to the other side as if I took a piece of paper and folded it around on itself. Well, these differ only in, this is the A and B bar form. This is A bar, B bar. So only A changes. So these from one side to the other are also logically adjacent. So the correct way to do this is to draw a circle that wraps around the edges. Now we can see that just the complement form of B is included in that circle. So B bar equals B bar. Well, we have the true and complement form of A, so don't need to include A in that implicant, and the true and complement form of C, so C is also not in that implicant. And we get the expression Y equals B bar. So a circle can wrap around the edges either right to left or left to right, and also top to bottom. So here we have the A, B bar, C bar, D bar minterm, and on the bottom we have the A, B bar, C, D bar minterm. Those differ just in the C, the form of C, the complement or the true form of C. So just in this position. So we can have circles that wrap top to bottom or right to left. So let's go ahead and enter this truth table into our K-map. So again, I'm going to draw these lines every 4 rows to keep us aligned and not make a dumb mistake of just entering it into the wrong box. So we're going to do 1 in the 0, 0, 0, 0 box, 0, and then we have the 0, 0, 1, 0 box here. In order to keep boxes adjacent, we have to jump to, when we enter it, to the bottom row. So 1, 0, this 1 here goes into the 0, 0, 1, 0 box, and now we have the 0, 0, 1, 1 box. Again, we have 0, 1, those ones are easy, and then we jump 1, 1. And now we have the 1, 0, we have to jump over to this column to start entering our information. We get 1, 1, 1, jump a row, 0, and now we go back to the 1, 1, 0, 0 box and continue entering our information. We get 1, or we get a 0 on that output, 0, 0, well, they're symmetric, but we'll do it in the right order anyway, 0, 0. Okay, so this is also a common error to enter the K-map incorrectly. So going from the truth table to the K-map and not doing that correctly. Okay, so we can now start to look at groups of ones. Again, the groups that we circle have to be powers of 2. So either 1, 1, 2 1s, 4 1s, 8 1s, 16 1s. In this case, we could have 16 1s. If we had 16 1s, the result would be y equals 1, no matter what A, B, C, or D is. Okay, so we start by looking at kind of isolated ones where there's only one possibility to circle that 1. So here's a 1 that's pretty isolated. There's nothing to the right, left, or top. So really can only circle the 1, make a circle going towards the bottom. So we try to make that circle as large as possible. This is tempting to do. But wait a minute, that's 3 1s. Can't do that. That doesn't work with combining either, right? We can't combine 3 things. We can combine 2 things. So we make that circle as large as we can. Well, that's as large as we can do it. That other one is a common error, but it has to be a circle that's circling a power of 2 1s. Okay, let's take a look and see some other possibilities. We have this 1 right here. Well, can't circle anything that way, or remember it can go around, or that way. So 3 of its directions are blocked by zeros. Can't make a circle like that. But right above it, there's a 1 that we can use combining with, so we can make that circle right there. And now we look at what's left. So we have this 1 right here. It's blocked that way. It's blocked that way. There's a 0 there. But we can go either down or right or both. In order to do both, there has to also be a 1 here. So in this case, in fact, we can make that as big as a circle that contains 4 1s. And now we look at what's left, and we have these 1s on the corners. Well, let's take a look at these for now. So the tempting thing to do is to say, well, let's see, this 1 could go either this direction or that direction. Okay, well, I guess we'll just choose one of those. I'm going to modify this in a moment. But let's say we just choose this. We say, okay, let's do that. And with these ones in the corner, we'll do that as well. Okay, again, that last step, The green circles I'm going to modify in a moment. But let's start with this and see what happens. So here we have a circle. It includes the complement form of A, true form of B. So we have complement form of A, true form of B. It includes both forms of C, so we don't include C in our implicant, in our product term, but just the true form of D. So D is included in our implicant. Okay, do a similar thing here with this red circle. True form of A, complement form of B. So we get A and B bar. And just the complement form of C. So we have C bar, but has the complement and true form of D in the circle, so D is not included in our implicant. Now we look at this circle. Well, this circle includes both complement and true forms of B, so B isn't in our implicant or our product term. But A just has the complement form, so we'll put the complement form of A into that implicant. And we look at that circle again. It covers just the true form of C, but both the true and complement form of D, so D is not in our implicant. So the implicant for the black circle is A bar, and C. Now we look at this green circle that goes from the top to bottom. It's a circle of two ones. We have the complement forms of both A and B, so we get A bar, B bar. We have both the true and complement form of C, so C is not in our implicant or product term. But we have just the complement form of D. We put D bar. Okay, and this other circle over here, again, a circle of two ones that goes from top to bottom, wraps around the edges. We have the true form of A, complement form of B. So we have A and B bar, and just the complement form of D. And we have the true and complement form of C, so C is not in our equation. So now we write all of these implicants down, and we write Y equals A bar C, or A B bar C bar, or A bar B D, or A bar B bar D bar, or A B bar D bar. So not too bad, except we may notice something about these last two terms in green. Well, those terms are almost the same. They differ in a single literal. This one has A ANDed with it, and this term has A bar ANDed with the term B bar D bar. So we could have used combining to get just B bar D bar. Combine those last two terms and reduce it to just B bar D bar. So what happened with the K-map? So remember that circles can wrap around from top to bottom as well as from right to left, or both. So this circle should have wrapped around both top to bottom and right to left. So it should have been a single circle that wrapped around all four corners. And then we get, well, just the complementary form of B. So we get B bar. Has both forms of A, so A isn't included in our implicant. Has both forms of C, complement form and true form, but just the complement form of D. So then we can also graphically get that minimized term B bar D bar. So remember that circles can wrap around the sides, both the top and bottom, and right to left, or both in terms of the corners. So if there are ones in all of the corners, as it was in this case, you can circle all of those ones to make a minimized term. So let's talk about don't cares. A don't care is a value that could be 1 or 0, but not both. It's either 1 or 0. It's not both 1 or 0, but it's either, so 1 exclusive or 0. It's either 1 or it's 0, but definitely not both. And we use the symbol X to indicate that it's a don't care. Some folks in some textbooks use the D symbol to indicate a don't care. We'll use the X symbol, which is also very common. So when does this happen? Why would we want to use a don't care? It seems like that might not be a good idea for a logic circuit. Don't we always care? Well, it could happen when we don't care what the output is in that condition. Or that input combination will never happen. So we don't care what the output is because it's never going to happen. Okay, so now let's look at the last rule for K-maps, which is circle a don't care, an output that could be 1 or a 0. Doesn't matter which, can't be both, but we don't care if it's 1 or 0. Circle that don't care if it helps, but only if it helps minimize the equation. So what does it mean to minimize the equation in terms of K-maps? Well, we minimize an equation by making the circles larger. The larger my circle, the fewer terms I have to include in that implicant, in that prime implicant. So this is a good chance to distinguish between an implicant and a prime implicant. A, B bar, D bar, those are implicants. They're products of literals, but they're not prime implicants because they don't correspond to the largest circle in the K-map. So again, these implicants here are indeed implicants. They're products of literals, but they're not prime implicants. The prime implicant is B bar, D bar. So here's an example of a function with don't cares on the output. So for some combinations, for example, the 0, 1, 0, 1 input combination, we have an output that's don't care. We don't care if it's 1 or 0. It can't be both, but we don't care which of those options it is. It can be 1, it can be 0. That input combination may never happen, or we don't care what the output is. Okay, so we'll take our truth table. We'll draw our lines under each 4 rows of the truth table to make sure we keep it aligned. And now we'll enter the truth table into our K-map. Remember the ordering, 0, 0, 0, 1, 1, 1, 1, 0. Again, 0, 0, 0, 1, 1, 1, 1, 0. In gray code order, not counting order. So we'll enter 1, 0, 1, skip a row, 1. 0, X, 1, skip a row, 1. And now we have 1, 0, 0, 0, skip a column, we get 1, 1, X, X, and finally we got our last group of 4, X, 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 X. Okay, so now it's a little more complicated than what we had before. I have to deal with X's as well as 1s and 0s. So I have basically 3 possible values of my output, 0, 1, and now this new variable or this new value X that could be a 1 or a 0. Again, you only want to circle X's if it helps you expand your circle for 1s. So you want to focus on the 1s. If the X helps you make your circle bigger, use it. Don't even look at the x's until you look at your ones. Again, you only want to use the x's, the don't cares, if they help you expand your circles that cover the ones. So when we first look at our K-map, a K-map that includes don't cares, we're going to ignore the x's, we're going to ignore the don't cares, and look at just the ones. So again, we want to start with the ones that are perhaps a bit isolated. So this one, for example, here, can't be circled out to the right or down, but it could be circled to the left here or up. Okay, so in that case, we want to look and see, well, could I make that circle of all four corners? In fact, I can. So to circle that one, to make it as large as possible, I will use this don't care, and by circling it, I basically make it a 1, but I only circled it because it allowed me to make that circle bigger. Okay, so we start with our first circle in our K-map, and now we can look at some other ones. So for example, we can look at this one here. This one is blocked going that direction. We can't make a circle going up because there's a 0 there. We could go left. There's a don't care there. We could go right, and we could go down. Okay, in that case, if we can go left, right, and down, now we see if we can make that circle even bigger. So we could do that, but if I use those don't cares on the right, I could make that circle even bigger. So that would be a common error to limit that just to that circle of 4, but I can make that even bigger using the don't cares just because it makes my circle bigger. Again, I'm looking at this 1, I'm trying to make the circle that covers that 1 as big as possible. I use these don't cares here to expand that circle to be even larger than it would be without the don't cares. Okay, so again, let me reiterate, this is the common error, to make that circle just that big and not use the don't cares, but we want to use the don't cares to make our circle as large as possible. And now we look and we see, well, there's just a lone 1 that isn't circled. So this single 1 right here that isn't circled. So now we look at the options we have. Well, we can't go to the right. We're blocked by that 0. It doesn't go to the right. But I could go up, down, or left. Okay, so if I can go in all 3 directions, I see if I can make that circle even bigger. So common error here is to do that, which is not bad, right? It's logically correct. It will give you the correct function that you want, but it's not minimal. I can use those don't cares on the left to expand my circle and make that circle that covers this 1 even bigger. Again, I use those don't cares just because they allowed me to expand a circle that covered a 1 that I was interested in. Okay, now the question is, are we done? There's still a don't care left. Do I have to worry about that don't care? Nope. This is where don't care is really appropriate. We don't care about that don't care. We only want to circle the 1s. If a don't care helps me make a circle larger that covers a 1, great. If not, don't include it in my equation. Okay, so that's a common error to do something like this, to include that don't care, or even worse, this. We don't want to do that. We want a minimum number of terms. We don't care if that output value at 0, 1, 0, 1 is 0 or 1. By not circling it, we define it as 0. It will output a 0, but we didn't care. And it doesn't help us make one of our circles that we need to cover a 1 bigger. Okay, so now we can write our implicants, our prime implicants for each circle. That prime implicant is A. We have the true form of A. We cover both true and complement forms of B, so B is not in the prime implicant. And we cover all forms of C and D, true and complement forms, all possible combinations. And so that term is just A. So the circle in red is A as a prime implicant. This circle on the bottom includes the true form of C only. So C is in our prime implicant. Includes the true and complement form of D. So D is not in our prime implicant. And it covers all possible combinations of A and B. So A and B are also not in our prime implicant. The prime implicant for this bottom circle in blue is C. And then finally, we look at the corners, just like we did before. The corners cover the true and complement form of A, so A is not in that implicant. Only the complement form of B. So this circle has B bar in it. True and complement forms of C. So C is not in the prime implicant, but just the complement form of D. So the complement form of D is in the prime implicant. And we end up with the equation y equals A or C or B bar and D bar. Okay, and again, we used our don't cares when they helped us expand our circle, but we didn't worry about covering them at all if they didn't help us. Well, what if I had written this as y equals A or B bar, D bar, or C, or some other way commuted those terms across the or operation? Doesn't matter. It's logically correct. So don't worry about what order you have those prime implicants in. Okay, so here's cleanly written for your reference and the solution. So a quick review of our K-map rules. Every one must be circled at least once. It can be circled multiple times, but must be circled at least once. The only reason it would be circled multiple times is if circling that one multiple times helped you expand your other circles. So every one must be circled at least once. Every circle must span a power of 2 squares in each direction, and each circle must be as large as possible to make it a prime implicant and not just an implicant. A circle may wrap around the edges, and we circle a don't care only if it helps minimize the equation. So in other words, only if it helps make a circle around a 1 bigger.